start from somewhere.
Yes.
Yes, let's start from somewhere. It's very nice to have Michal Malinsky back in Valencia. Most of you know that he did a postdoc with us. He had a Marie Curie fellowship, and he left us nearly 2 years ago.
I think it's more than 2 years.
2 years ago. Now he's back for a short visit just this week, and we asked him to give a seminar, and he talked about proton decay today.
Yeah, it's my favorite topic. But actually, this time it's somewhat unique because, but there are two unusual things about this. Because first, it's the 28th of October, and that's the day when almost no theoretical physicist in the Czech Republic works, because that's a Czech public holiday. We are celebrating the anniversary of the founding of the Czech Republic, well, actually, former Czechoslovakia in 1918. So I'm supposed to be somewhere else, but I'm so happy to be here, of course. And second, I'm too young for really giving a good overview of what happened in the 40 years with this grand unification. I mean, Roberto said mumification, but unification is still somewhat better. Although, I mean, you make your own decision at the end, because this talk is going to be maybe slightly pessimistic, but never mind.
Do you have to exchange the speaker with Professor Hirsch?
No, I think Martin would refrain to talk about leptogenesis, which I will mention. Okay, never mind. So, but what I'll be talking about is actually perturbative barrier number violation in particular. By perturbative, I mean everything which is not in the standard model. As you know, in the standard model, what's this? What's in the standard model? Well, there is actually baryon and lepton number violation in the standard model, but it comes only at the non-perturbative level. So I'll just give you a very brief account of this initially. Then I'll go to the lepton number violation, because that's something which is somewhat more naturally embedded into the standard model or its simple extensions. And then finally, I will go to the perturbative baryon number violation and ground unifications as perhaps the most plausible framework for such things. And then I'll tell you something about the 40 years of unification, which is the roller coaster part of the presentation. As you will see, there were many, say, triumphs and depressions throughout the last 40 years. And then at the end, I will just try to account a bit on discuss a bit the quality or the accuracy with which you can ever think of, in relation to proton lifetime estimates. And this is the pessimistic part. But then, well, let's start with this non-perturbative baryon number violation. It's related to the chiral anomalies. As you know, there are symmetries which can be anomalous in the standard model. If these are local symmetries, that's really bad, because then you have amplitudes which are gauge dependent, or the theory is non-renormalizable, etc. So you don't want chiral anomalies to happen with symmetries related to this generated T, which are local symmetries. But as long as you consider global symmetries in the standard model, those can be anomalous. And actually, there are many examples, especially in the strong interaction part, where anomalies in the global symmetries are really vital for the standard model to work. But I'll be talking about the lepton and baryon numbers. And as you know, like both these global symmetries are anomalous in the standard model. There is one combination which is not anomalous, that's the difference. But of course, then the sum is anomalous again. And if you have such a non-conserved current, then of course you can ask yourself what happens, what does this imply physically? And as long as this current is associated to the global symmetry, and the global symmetry does not have a Goldstone associated to its spontaneous breaking, then this is almost no problem, because it comes at the effective level only as a total derivative into the Lagrangian, so you will never see that thing in the perturbation theory. But you can see this at the non-perturbative level. So, for instance, I mean, if you really calculate the change of B plus L throughout some kind of system evolution, what you get is this formula where the change in the B plus L is associated or is related to something which is called the Chern-Simons numbers of the theory, which in the pure gauge theory is something like this. So some integral over this funny combination of gauge potentials. The point is that actually these gauge potentials in the Young-Mills, in the non-abelian theories, they may have a very rich topological structure. The theory possesses kind of disjoint sectors, well, this is pretty similar to the solid-state physics, where with say periodic potentials. And if you look at the ground state, it's something like a superposition of localized states. I mean, states localized here. It's called a theta vacuum. And the point is that you can encounter tunneling between different kind of settings which correspond to this kind of configuration to such a configuration. And each of these configurations is characterized by something which is called the winding number. And this and the Chern-Simons numbers are essentially, I mean, for the SU2 are essentially these winding numbers.
Why do we have more than one type of Chern-Simon number?
Well, because each of these is, well, this is the SU2 part and this is the U1 part. Here you see the SU2 gauge potential, and here you see the U1. Actually, it's only this piece which really matters.
Yeah, that's what I was...
This is, well, as long as these states are concerned. So, and you can actually see the structure here. You see three terms which are pure gauge here.
Yeah.
So, and you can calculate...
It's a pure gauge, but you cannot rotate them.
Yes, yes. And actually, those processes in which B plus L changes correspond to the tunneling from one wave, this is called a Bloch waves usually, to another one. And of course, in order to calculate something, you have to calculate the probability of these transitions, which is something associated to the so-called instanton, which is nothing but a solution which interpolates between these two minima in the Euclidean regime. And the action of the instanton then gives you the amplitude of the probability, which is terribly, terribly small if the system is non-thermal. If it's at a zero temperature, that means it sits very close to those dips. But nevertheless, there is like a fancy effect. This can have at the standard model level at zero temperature, and that's this kind of decay. I mean, this is perfectly allowed in the standard model. Of course, you will not see it because the rates are this small. But in the thermal case, where the role of instanton is played by something which is called a spall level, these transitions can be pretty fast because you don't need to penetrate through the barrier, but you can jump over it. And that's what underpins the leptogenesis mechanism, where you first generate a net lepton number, and then you kind of transfer it by these spall levels to the barrier number as well. So this is how it works in the standard model. However, there are good arguments in favor of perturbative lepton number violation in the standard model. So now we are from non-perturbative to perturbative. And let me just present this very simple and then kind of, some people say it's a bit fishy, but nice argument, just stating that charge quantization neutrino masses imply perturbative lepton number violation to some extent. How does it work? I mean, by charge quantization, I mean this simple mechanism that tells you that in order to cancel all the gauge anomalies, those unwanted anomalies that would lead to gauge dependence of your amplitudes in the theory, you have to make sure that all anomalies associated to all gauge symmetries in the standard model would vanish. Well, actually, there's a trick. You don't need to consider all of them. It's sufficient to focus on these two and take into account the constraints that you get from the Yukawa sector. So I will consider only those two from this sector which are non-trivial. And they give you these relations between the hypercharges, which we assume to be unknown, of the left quarks, left leptons, and these are up-type right-handed quarks, down-type right-handed quarks, and charged leptons right-handed. So these are the two formulae from really the anomalies. The rest comes from the existence of the mass terms. So that means extra three constraints. Otherwise, you would never be able to build such terms in the Lagrangian. And if you solve this, you get something like this, provided that you fix your normalization by fixing the Higgs. I mean the Higgs hypercharge. But this is a solution which is unique. And of course, I mean, it looks kind of fishy that I did not. I mean, this is kind of scattered. There's something missing, of course. Now, if you assume that there's not only those 5 fields that I was talking about, but there's also the right-handed neutrino in order to make Dirac masses, then you have an extra unknown hypercharge which enters all around here, in particular here. Of course, then there is an extra a relation like this because you also want the Dirac mass term, and then the solution of the same system, although you have one more equation here, is no longer discrete. I mean, because this and this become dependent. I mean, they are linearly dependent modulo using all the other equations here. So, if neutrinos are Dirac, that means if you assume there is the right-handed neutrino and try to solve the charge quantization system again, then you see that actually this becomes a one parameter driven set. So, well, in order to understand this, there's a simple argument that in the presence of the right-handed neutrino, there is another symmetry that can be even gauged, and that's the B minus L, because in the presence of right-handed neutrino, this is also zero, right? Without the right-handed neutrino, this is not zero. So, if there is right-handed neutrino, the B minus L is a perfect gauge charge, which can be summed with arbitrary real factor with the previous hypercharge. And you can kind of smear the hypercharge as much as you want. And this epsilon is related to this unknown hypercharge of the right-handed neutrino like this. And the point is that there are strong constraints, strong experimental constraints on this epsilon, because in the presence of such an epsilon, well, the hydrogen atoms would look the same because the same effect on protons would be compensated by the effect on the electron charge, but not the neutrons. The neutrons will no longer be neutral, really. And just from the neutrality of matter, you get this kind of a number. Right? So one can even say that to such a level, or either you accept that this number just fell from heavens, or you are on the verge of saying that maybe neutrinos are not really Dirac. So this is how this simple argument may be phrased. So, and of course, if neutrinos are not Dirac, then they should be Majorana, and that means that there is such a term in the Lagrangian, and that means if there is such a term in the Lagrangian which violates lepton number, of course, that there is perturbative lepton number violation in, of course, the beyond standard model physics somehow. So all I wanted to say here is that if you cherish the mechanism of hypercharge quantization in the standard model, which works perfectly as long as you don't consider neutrino masses, and you want to kind of make use of it at the level of the simplest conceivable standard model extension with massive neutrinos, then you better look for extensions in which your neutrinos are Majorana. That means perturbative lepton number violation. And indeed, like if you look into the history, lepton number violation is not something. I mean, it's a very old story. Even the first oscillation paper by Pontecorvo was actually considering not this kind of standard neutrino oscillation as we know it nowadays, like between flavors, because there were no other neutrino flavors known back in '57. Mu neutrinos were only around since 1962. So in his case, it was really neutrino anti-neutrino oscillation, which, however, differs considerably from the flavor oscillations because there's this extra helicity flip that you need to have. So you have got this extra kinematic factor there, and it tends to be strongly suppressed because we know nowadays something about this, and for the technical energy, this is usually strongly suppressed. So this is a reference where you can read more about it. At the level of the effective operators language, I mean, that's how you parameterize the unknown physics at the standard model level. That means dimension higher than 4 operators. We are actually encountering the very effects of lepton number violation at the dimension 5 level, which is the super famous Weinberg's operator, which from various constraints indicates that this effective scale should be somewhere in this ballpark. This is mainly from cosmology, from tritium decay, and also, of course, from the oscillations. The point is that actually there is only one such a dimension 5 operator in the standard model. So if you accept that neutrinos are massive and that there is perhaps perturbative lepton number violation, you are perfectly fitting this kind of quest for beyond standard model physics in terms of higher order operators. So in a sense, we've just made it to the first non-trivial level at the ladder of higher dimensional operators in the standard model. So this is dimension 5. There's only one dimension 5 operator. By the way, it's good that we have the complete Higgs doublet nowadays, because without that you cannot write it. I mean, I think there's no one who is really kind of unhappy about Higgs being written like this. Some people really prefer this this Anderson, Brown, Egler, Higgs, Brown, Hagen, Kibble, Weinberg. If you prefer that, then you read this with capitals and it's highly interacting gluon produced scalar. That's the kind of old joke there. But never mind. I mean, let's try to go to the dimension 6, because we've just exploited dimension 5. Let's go to the dimension 6, and that's where you encounter perturbative barrier number violation in standard model. There is something like 59 operators at dimension 6 in the standard model. It's just part of them. You can see that, well, some of them are kind of familiar, some of them are not. I think these are pretty familiar because these correspond to anomalous couplings, I would say EDMs and G-2 and things like that. But what I'm really concerned about, I mean, these are the, these are interesting for flavor physics. These are the direct Fermi, 4 Fermi interactions. But what we are going to be interested in are these 5 operators here, because those are the final number violating dimension 6 operators in this standard model. For example, I mean, the question now is, of course, how such operators are realized at the renormalizable level. I mean, in other words, what's the beyond standard model renormalizable theory that can give rise to such operators at the effective level? So you're asking the same question that Schwinger and Glashow asked back in the 50s about, say, dimension 6 operators describing neutron decay, muon decay, whatsoever, and about the underlying dynamics. So we are asking ourselves now exactly the same question. So that means, well, the question is how to actually, say, open these operators in such a way to get renormalizable dynamics. So for instance, if you write, I think this is the first one here, if you write it like this and you open it here, you get a scale exchange. So you need an extra scale which transforms like this under the standard model in order to really generate this operator when you integrate out such a scale. But you can fuse this and you get immediately a vector exchange which leads to the same type of an effective operator. So I will call these deltas, these x's. Okay, what do we know about such operators from the standard model perspective? Well, these operators would, of course, since they do not conserve barrier number, and they are very special in the sense that they conserve B minus L. So there is a typical class of processes these operators would be responsible for. And this is in particular proton instability. I mean, that's the old story of proton lifetime. Today's numbers indicate that it's longer than 10 to 34 years, which immediately puts some constraints on the masses of these mediators here, and tells us that such a new physics, I mean, these guys should not be below 10 to 15 GeV, something like that. However, this is really a huge and very remote scale. So the question is, can we learn something about such a scale from the standard model perspective? The answer is yes, we can. Because this is something that the renormalization loop does for us. Of course, this is a formula that everyone of you knows. So the question is, what happens there in the standard model given these formulae? Just looking at the gauge couplings, and this is the famous picture. I'm not putting any U1 because there the normalization is not very clear. But the point is that in the pure standard model, the gauge couplings do like this, and they intersect somewhere here at around 10 to 16 GeV, which is remarkably close to that limit derived from the proton lifetime, which is 10 to 15 GeV approximately. So it tells us that if such a dynamics occurs somewhere, it should be very close to where we can look nowadays. So this 10 to 15 is the experimental limit nowadays, and this 10 to 16 is the theoretical number. So these two numbers are very close to each other, and it gives us a chance to really observe something, if there is, of course, something like that. Of course, in order for this to make sense, one has to see all these, a specific type of behavior behind this intersection. And the remarkable thing is that if you just add to the standard model that x field, that x vector and delta, what you get is this. So the B coefficients of the beta function is just homogenized. And that means that if this happens exactly at this scale, in other words, if the new dynamics takes place here, then from here on there seems to be a single gauge dynamic, a gauge dynamics based on a simple gauge group, rather than the 16 GeV. And that also tells us the barrier number violations. And not only the scale, but also the strength of the coupling which enters at least those gauge boson-driven transitions, which is perfect. I mean, in a sense, the theory tells you a lot even before you start thinking about what it could be. So this is the idea. This is behind the idea of granulifications. So just to flesh this, the granulifications are spontaneously broken beyond standard model gauge theories based on simple compact gauge groups which are larger than the standard model gauge group. And in particular, these are supposed to be the theories of the dimension 6 barrier number violating operators by exactly by the very mechanism I was just describing. And of course, other stuff like magnetic monopoles, charge quantization, which you can, of course, implement in the way I showed you, like via anomalies in the standard model. But there, you don't quantize the charges for vector-like multiplets, for instance. But here, you get a complete charge quantization. Vector number violation, because the guts, especially the SO thing that's typically contain a seesaw mechanism in some way. Okay, but this is general. That's how it began. That's a paper on the 25th of February 1974 by George A. Glashow. By the way, 25th of February is another very important date in the Czech history, but that's not as bright as the formal one. On the 25th of February 1948, we had the communist putsch that kind of changed the way of, the direction of the country for about 40 years. So this is a sad date. But, well, never mind. Like 1974 compensates it because that's the golden year of the particle physics. So let's be generous and forgive George A. Glashow that they published it on the 25th of February. So what they said was actually that there is a unique scheme conforming all these requirements I commented on before. At the level of the rank 4 extensions. That means if you take all simple groups of Lie groups of rank 4, then you find only SU5 as a good candidate for this kind of unification game. How does it work, or how did it work back in 1974, when the third generation was totally unknown, and not even the C-core was known in February, but nevertheless, once you start classifying your fields with respect to a bigger group, then you have to, of course, cluster those known fields at the standard model level into something which are representations of these bigger groups. That means, for instance, the vectoric doublet and BC would go to the 5-dimensional vector representation of this guy, and the other 3 would go into the 10-dimensional antisymmetric tensor, etc. Of course, since you have a bigger gauge group, then you have also a bigger gauge sector, because you have to have the complete adjoint of the SU5, which is 24-dimensional. So besides the gluons, A fields, and B fields of the standard model, you've also got these extra X gauge bosons. Those are exactly those that I was talking about when we were opening that the dimension 6 operator. And you also need, of course, the Hicksology somehow besides the standard model Higgs, which is a doublet in the standard model, which must be then, or which should be then, embedded into the full 5-plet of the SU5, which, by the way, gives you exactly this delta scalar, also responsible for the dimension 6 operator. There is a need for another scalar sector which will take you from there to there. So an extra gut-breaking scalar, which is due to the rank considerations typically taken to be the adjoint, but there are other options like 75 or so. But this is just the simplest George A. Glashow model. And from there, actually, the story begins. Well, this is actually the graph, which should resemble the roller coaster. And this is the number of citations of works in spires. But this is, I think, only SO10 works, because you can't see the Georgia glacier here. This is something I got from Luca Di Lucio. He knows how to dig out these data from spires. I don't, so I could not update this for you for the SU5s. The blue curve is the total, and the blue histogram is the total, and the red is the SUSY, supersymmetric. So you see that around around those days, the majority of the papers was on SUSY. Here initially there was no SUSY, so all of that was in blue. So after this infancy period, which was mainly driven by the fact that already those days the proton lifetime was assumed to be bigger than 10 to 30 years, which was remarkably close to the theory calculation by Quinn, Weinberg, and George back in 1974. But this is of course just a very rough estimate. I mean, and of course these numbers are enormous, so people needed large detectors. So this is actually when this first kind of or not a renaissance yet, but I mean when the interest in these theories really grew exponentially, at least initially. But of course then there was a depression. So how come there was such a depression all of a sudden? It was not all of a sudden. It was related to observation, of course. And well, the cheapest detectors of you need to observe huge amounts of material at once in order to have ever a chance to see something like a proton decay. So typically you also need a transparent medium in order to be able to propagate a signal from where it occurred to your detector, because you cannot have like a huge, enormously huge, this is kiloton scale detector which is active in the whole volume. I mean, which can read data from the whole volume. So that's why it's usually done in water or liquid argon or in liquid scintillator environments. And what's being looked for is, in particular, this golden shell process where proton decays into pi 0 in plus, for instance. And this is really a gold channel because, of course, we've got the two prompt gamma photons, very strong gamma photons from the pi 0 decay, which, of course, like in the water environment, they would immediately develop a very strong electromagnetic shower. And then after this positron gets stopped somewhere in the medium, it gives you two prompt gammas. So these gammas would be yeah, and also that you would detect. But there's another thing. Before it gets stopped, it's shining a chunk of light, because that's a positron propagating at a very large velocity through the medium. So this signal is pretty unique and very nice, and there is a lot of information one can dig out from such a signal. This is a typical say, shape of such a signal in a real environment. This is a super K simulation, I think. So I think this is from the positron, and these two cones are from the two gammas from the pi 0 decay. So it's also a pretty clear environment. But yeah, well, initially the super K or the Kamiokande was even built to look for the proton lifetime, of course, but then it turned out to be a great neutron physics machine. There's a silver channel which corresponds to the decay into kaons. Unfortunately, unlike the E plus in the golden channel, kaons do not shine because their energy is below their. I mean, they are not very relativistic because the mass of the kaon is about 490 MeV. So there you have to look for the secondaries, and either you look into this or this channel. In both cases, the signal is not so clear and not so pronounced as in the golden channel. So usually the sensitivity in these kaonic channels are like an order of magnitude worse than in the golden channel. And of course, there's a lot of other channels that one should think about, but I don't have time for it. So let me get back to this roller coaster picture. These all really kind of rocketed in the 80s until, and well, there's this kind of funny picture which is the front page of the first of the proceedings of the first workshop on unifications in 1980s, until there was this, until about 1990s, where there's this Great Depression. And this is related to the fact that there were relatively good data by then from the SPS, which revealed that actually gauge unification in the simplest SU5 model does not work really well. And the reason is that, with the data, this picture became rather clean, and it was clear that the U1 does not meet with the other two. There's this kind of triangle of death instead. This, of course, all assumes nothing going on between the electroweak sphere and the gut sphere, so this is the kind of big desert picture which many people complain about. But never mind, that's the status of the minimal SU5 model. And in the minimal SU5, as I said, you have a very limited number of options of how to break it. So there's not, the minimal SU5 is in a sense, say, predestined to have such a desert. That was also the reason why people, Paul Frampton wrote this kind of proceedings on the last workshop on unification in '89. So we are here. But then, of course, those data, the same data was reinterpreted as an indication for low energy SUSY. So there you see the new peak, which I call the SUSY frenzy peak, because indeed, like if you do SUSY, that means the standard model plus X and delta, and the T scale SUSY, what happens is this. So this is a very famous thing. It looks rather attractive, and also those days one saw one can see the first, to some extent, reliable calculations of proton lifetime in the supersymmetrized versions of the SU5 model. Unfortunately, again, like even this simple SUSY SU5, although it was pretty consistent with the gauge unification, it was in trouble with the proton decay, because there is a huge correlation between the flavor structure of the effective dimension 6 operator and the masses of quarks and leptons. So that model was really strongly constrained, and it was claimed back in the 90s that it was actually not consistent. However, until now, there are still disputes where this is a firm statement. There are many people still working on, even on this minimal SUSY SU5, and the situation is not entirely clear. Never mind, this observation caused the second depression due to this dimension 5 proton decay, because in SUSY, proton decay is due to dimension 5 operator, not dimension 6. And people didn't know what to do until about the beginning of this millennium, when Super K and other neutrino experiments actually brought in new inputs from mainly on the flavor sides from neutrino oscillations, etc. And this is something I would call the SO10 era, because again you see this peak in citations of the SO10 papers. Sorry, in the production of the SO10 papers. And as I said, SO10 somewhat fit very well to the implementation of the seesaw mechanism. So somewhat SU5 is diminishing, and SO10 was kind of rocketing again. But never mind, actually I could not really prolong this because I don't have the tools, but I suspect that this is even less than steady here. So if someone who knows how to do such things, maybe Roberto knows, I'd be very grateful that we could have an updated figure here. I don't. Whatever actually happens here is irrelevant to this, to the considerations about the accuracy of possible calculations of proton lifetime, especially in the view of this new generation of megaton scale facilities that we are maybe about to face in 10 years from now, be it the Hyper-K or LBNE. Well, LBNE is not going to be megaton scales. I think the agreement is to build it on the ground in the first phase with about 35 kilotons of liquid argon, so maybe LBNE should not be counted here. But in the initial design, which was underground and somewhat bigger, it would fit into this category. No one really knows, or maybe someone knows here, whether LENA is going to be built. There was this kind of withdrawal of the Finnish side from this project in the PSLV mine, but I heard some rumors that they are reconsidering it again, and maybe LENA may be built there in Finland. So, but Hyper-K is somewhat like on a good track, I would say. There are regular meetings, and the collaboration is growing now. So let me focus on the Hyper-K. However, I mean, whatever will be done, there's no chance actually with the new generation to get more than about an order of magnitude better constraints than what we are now getting from Super K. So, I mean, the improvement window is pretty shallow. It's only one order of magnitude. That's the experimental side. On the theory side, we are now in a very good, say, place or very good moment to try really to do some kind of a reliable calculation. Because the standard model is firmly established. We've measured many parameters, I mean, most of the parameters of the standard model with a relatively good precision. So if there was ever time to try to calculate proton lifetime with an accuracy which would maybe fit within this improvement window, of course, if your accuracy is this big, then you will never learn anything from such an improvement. Unless you really observe the signal, but that would be so striking that now no one would really care about such pictures. But suppose there would be no signal or just kind of a hint. Can you learn something from there? Yes, but only if your theory can fit your Gaussians within this window, so to say. So that means, however, that you need a factor of few precision in the calculation of the proton gate. This is something which was bothering us, bothering me and many other people for years. So I'll be talking about this very issue. The quality of the existing proton lifetime estimates, as I anticipated, is really poor. You see, there are many orders of magnitude. I mean, they are stretching from 10 to 28 to 10 to almost 40. So these are no real predictions. You cannot really learn too much from the non-observation of the signal at Hyper-K if this was the quality. Although the current limits make it somewhat more narrow, but still these stretch over many orders of magnitude. The problem with all these, I mean, there are like 3 or 4 factors that strongly limit the accuracy of any theory account of proton lifetime or proton decay estimates. One of them is that you need an extremely good gut scale determination. You need to know very well where those extra guys, this delta and x, those leptoports, where they live, because this information about their masses enters into gamma, into the width, as the 4th power. So this really is a vital piece of information. Unfortunately, I mean, the gauge couplings tend to intersect. Well, the intersection of the gauge couplings is usually the point where this mass is, right? So you have to do a very good analysis of the gauge coupling unification pattern and check where the intersection point is, or something which resembles the intersection point at the 2 loops, because at 2 loops there is no intersection really. There you have to take into account threshold effects at the gut scale, and it kind of smears the single point unification. But never mind. The point is that you have to calculate very well the mass of those vector-like or scalar mediators. And this is really kind of tricky because those curves tend to converge under pretty shallow angles. And if there is a convergence, I mean, if this is so shallow, then any error, or even a small error on the vertical position makes a large error on the horizontal position. So this is what I call a scissors effect. Like if the scissors are I mean, if you push the scissors, then this intersection point runs very fast, although you push just a little. So this is the main uncertainty. This is all theoretical uncertainties. And actually, I think there's even no way to do this ever in supersymmetry. And okay, maybe I do have time to tell you this. Like, many people, when I say I want to do non-SUSY cuts, many people would just jump into my face and say, well, what do you do about the hierarchy problem? Come on, how could you even think of unifications without supersymmetry? So my answer is here. Actually, I think that the standard argument about the hierarchy is wrong. I mean, that argument that the Higgs mass suffers from large relative corrections. And the point is that if you really look into what you are calculating by those famous loops on the Higgs propagator, so you take typically a heavy state, a heavy scalar, for instance, here, and then you encounter this quadratic divergence, this quadratic behavior, quadratic corrections, which is say polynomial in the mass here. Then you say, well, I mean, my Higgs mass is quadratically sensitive to the large-scale physics, and this is really bad. I mean, how could that be? So you better say ask someone to regulate this quadratic behavior, because if you do not do anything about this, the root of the two-point function shifts really by this quadratic amount, and that's what people call the hierarchy problem. They usually evoke SUSY to give you the opposite sign correction, which just cancels this one. So this cancels this to a large extent. So that's one of the arguments in favor of the low energy SUSY. But actually, the devil is in the detail, because what you are calculating here is not the Higgs mass. This is a correction to an unphysical parameter. Because with just these graphs, your perturbation theory is contrived. I mean, you should better watch what does not only the two-point function, but also what does the one-point function do. Because if the one-point functions in your perturbation theory are not zero, then you can hang them on any diagram. I mean, you can always like make this diagram kind of furry by attaching non-zero one-point functions everywhere. So you better first ensure that you are in a perturbation theory in which the one-point function is zero. But if you do that at the same level of precision as here, then what you see is also a quadratic divergence or quadratic sensitivity of the one-point function. Right? So the question is, if I shift from the tree level to the one-loop vacuum, what would happen actually with this Higgs mass? Because the pole of the one-point function can be interpreted as a Higgs mass, or as the mass of that guy, only if you are really in the minimum of the scalar potential, which is indicated by the zero of the one-point function. And what happens is that these two quadratic sensitivities just cancel each other, and there is no such a quadratic sensitivity to the high-scale physics in the physical Higgs mass. So the Higgs mass really depends only on the Higgs scale, and maybe logarithmically, but in a way that even the logarithmic dependence decouples. So in a sense, the Higgs is in exactly the same shape like anybody else in the standard model, because its mass is also governed by the electroweak scale. If that was not the case, you could decouple the Higgs from the standard model, which of course is impossible because that would render the standard model non-renormalizable. So in this case, in this sense, I don't care that much about this kind of stipulated quadratic dependence of the Higgs two-point function, because it does not enter the physics. I mean, physics is correlations, and all this quadratic dependency drops when you do correlations, when you really do physics. So there is a quadratic sensitivity, but only in the VEF, which is not a physical parameter. VEF is something which is skin dependent. So who cares? If you ask yourself a wrong question, or if you ask the quantum field theory a wrong question, then you better get ready for a wrong answer, or for nonsensical answer. But if you ask the right question about correlations, then there's no hierarchy problem whatsoever. So this is my maybe extreme account on the hierarchy business. But the bottom line is that I will not care that those unifications that I will be talking about in the rest of my time are not supersymmetric. I'll be happy that they are not supersymmetric. Okay, coming back to the accuracy of the proton lifetime estimates, there are of course other sources of uncertainties here. This next to leading maybe in the conservative guts, so to say, is the flavor structure of the baryon number violating currents. So these coefficients, those are the coefficients of the dimension 6 operators, which of course do depend on the rotations from the current basis to the mass basis. And you don't know too much about them because they contain right-handed rotations, which we have no access so far from the low energy point of view. So the only thing that you can do about this uncertainty is really to use the correlations between Yukawas that you do have in the gut theory, because in the gut theory, different fermions are accommodated in bigger representations, and like a single Yukawa coupling in the gut gives you or drives many or more Yukawa couplings in the effective theory in the standard model, so to say. So you rather go for a gut which has a relatively simple Yukawa sector, otherwise there will be too much of a freedom here in these coefficients, and you will again not be able to do too much about proton lifetime. But maybe the main killer in really most unifications are the Planck scale effects. Since the gut scale is so close to the Planck scale, 10 to 16 is very close to the 10 to 18 of the reduced Planck scale, you should not really forget about possible Planck scale generated effective operators. And this is the main culprit. This is a really evil operator. This is F mu, these are the gauge field tensors. And this phi, this stands for the scalar which breaks the gut symmetry. In the asymmetric phase, such an operator actually kicks your gauge kinetic form. You see, if this becomes 10 to 16, this is 10 to 18. This is a one-person correction to the gauge kinetic form. And in order to make sense of the perturbation theory, you have to canonically normalize. But that means you also have to change the definition of the gauge couplings, because your covariant derivative should be the same. And that means such operators, although we know nothing about them, they would smear the definition of the gauge couplings. So you don't know how to define the gauge couplings properly, and the less you know whether they should meet like this or like this or like. There is something like an irreducible shift to the gauge couplings induced by such Planck scale effects. And as I said, if you have this an uncertainty in the vertical position of the gauge couplings, the Caesar effect would induce a large shift, or can induce a large shift on the gauge on the gut scale. That means on the mass of those mediators. So this is really something which kills any considerations about precision in most unifications, because you cannot, unless you have a theory of gravity, really, you cannot estimate the size of this effect, of this coefficient, this lambda. Especially in SUSY theories where there is a lot of extra degrees of freedom, this lambda is not even the Planck scale. Like if you couple theories which are very rich on the field content to gravity, then the effective cutoff of such a theory is even lowered with respect to the Planck scale. That's, you can read about it here, for instance. So these effects become very, very important. You should not forget about them. However, there is an exception. As to any rule, there is an exception. And that's the case when you consider the SO10 theory, in which the large left, this potentially dangerous field, which has a large 10 to 16 GeV left, is the 45, the adjoint of the SO10. Because in such a case, if there's 45 here, this is also an edge joint representation. So it's 45 times 45 times 45. And this is 0. Because 45 is anti-symmetric in the group space. This is a special feature of only this edge joint representation. So what this tells us is that if you ever want to calculate proton lifetime at a better than the leading order precision, there's only essentially one, at least one, the only one I know of, settings where it makes sense, and that's this SO10 broken by 45. This is an old story again. I mean, such a simple model has been considered before, of course, back in the 80s, and it was one of the first options to be ever considered because the 45 is really a nice way to break the SO10 down to almost the standard model. And okay, this is how the waves look like in the 45. 45 is an anti-symmetric 10 by 10 tensor. The minimal model looks ugly though. I mean, there's more than a billion terms here if you really expand all these summations over all the indices here. But never mind, the number of parameters here is pretty limited. It's about a handful, like, or a dozen, something like that. So it looks terrible, but it's not so bad. Nevertheless, people usually call it a nightmare. The main concern, or the concern here, the real concern, is that it has been ruled out in the 1980s. And it has to do with these two scalar masses. I mean, if you diagonalize that potential there, you end up with a list of masses in terms of those parameters in the potential and the waves there. And this is a pretty dangerous set because it tells you that there are tachyons. At least one of them is tachyonic whenever your omega r and omega y are not far from each other. Are far from each other. In order for these not to be tachyonic, none of them, you have to be, I mean, these two omegas should be very close to each other. But these two omegas are those two sets of waves. And if they are very close to each other, this is almost uniform, and you are breaking in almost perfect SU5 direction. But this is pathological because the SU5 does not work in the non-SUSY case. So there's no way really to consider this to be a realistic scenario in non-SUSY. However, this was all based on the leading order approximation, I mean on the classical potential. So, and as classics say, we should not trust arguments based on the sort of perturbation theory. This is the second Weinberg's rule of progress in physics, or the second Weinberg's law. It's like the three Asimov's laws in robotics, so this is the second Weinberg's law. What we did in 2010 was that we actually calculated those extra radiative corrections to those potentially dangerous tachyonic masses, and we found that they are positive at large, in principle. So you can have this omega r and omega y far from each other without ever encountering the tachyonicity problem. But you have to work at the quantum level. So that's another nice thing about this minimal SO10 unification, that it's really entirely quantum. It does not make any sense at the classical level, but at the quantum level it makes perfect sense. And it's also the reason why it was not considered for almost 30 years, since the 1980s, when it was kind of ruled out on the classical level. It was not considered until 2010. So there's a lot of room still to work there. And if this was not the case, I would totally abandon unifications. I mean, if this was not such a special model, I would not waste my time on it. But it is special in a sense. So the question is, okay, if the Higgs model works, is there a way to really implement it in a physical theory? In other words, to really try to build a model in which this 45 breaking takes place and it's stable at the quantum level, etc. And that's what we tried. Actually, we had to try pretty hard, because if you just look into old papers about the breaking of the SO10 gut symmetry by this edge joint representation, what you encounter is that typically your seesaw scale is at the order of 10 to 10 GeV, which is pretty low, because what you need is something like 10 to 13, then 14. So this in such a case, that would predict two large light neutrino masses. And you have only two options. Well, you have only one option essentially if you accept this. And that's the multi-Yukawa fine-tuning. You would have to take your Dirac masses and down-tune them a bit in order to be happy, to make the light neutrons happy with this relatively low seesaw speed. But this is a multiple fine-tuning. You have to fine-tune several parameters in the Dirac sector in order to accommodate neutrino masses. And this is not what we want, of course. We don't want to save this model with so many fine-tunings. Of course, like this very number here it can also be say seen as a fine-tuning because this is a scale which is much below the gut scale. But this is only one fine-tuning, and we would happily live with such a single fine-tuning if the Yukawas were not to be fine-tuned anymore. But actually, you can do this single fine-tuning elsewhere. You can try to keep the seesaw scale close to the gut scale at 10 to 14, and it would be very good if this can be achieved with only a single fine-tuning and everything else would be consistent. And that was the question that we asked ourselves in 2012 of whether there may be some kind of alternative scenarios where seesaw scale is pushed automatically up and there is no need to fine-tune the Yukawas then, but again the gauge coupling unification can be safe. And indeed there are two such options. The more interesting one is actually having a light scalar with these quantum numbers, so it's a color octet SU2 doublet and hypercharged charged scalar. And by light I mean really TeV-ish. So this is the situation like a correlation between the gut scale, that means proton lifetime on the vertical, and the mass of such an exotics on the horizontal. And you see that the lower you get your exotics, the longer proton can live. So these cuts are by the different numbers that you can. This is the super K number, and these are the two hyper K numbers. So what this tells you is that if hyper K doesn't see anything like this until 2040, this octet should be below 10 to 7 GeV, which however is pretty high. Nevertheless, if you do the same thing at 2 loops, okay, so this is the shape of the interesting region at 1 loop. If you do the same at 2 loops, you get this. So this dark edge here shifted by 3-4 orders of magnitude. So this is the situation at 2 loops. So here one can repeat again the claim that if no proton decay is seen at hyper K until 2040 or 45, now the schedule is shifted, that should be below about 10 to 4 GeV, which is 10 TeV, so maybe few tenths of TeV, which in principle, I mean, if we are just lucky, maybe even revealed at the not at the LHC, but maybe at the next large hadron collider. So maybe if we are lucky, it's the solution is here, and you would see. There's the other case. I mean, there is a second case which corresponds to the color sextet SU2 triplet and charged under the hypercharge again. This is our last very recent analysis, and it looks like, well, it looks like this. This is again the gut scale. This is the mass of the sextet, and you see that the sextet is not very light. I mean, it's really towards the high scale, but so it looks like uninteresting from the low energy point of view. But actually, the interesting thing is that this may be pretty constrained by the flavor fit. So because in order to reach this region, you need your seesaw scale to be relatively low, and in order to so the seesaw scale, if you for instance assume the seesaw scale to be above 10 to 12 GeV, which has to do with the flavor fits, if your seesaw scale is too low, then you cannot fit the flavor. Then you cut out this part of the picture. So it looks like that this solution, the second minimally fine-tuned solution, is actually, or could be inconsistent with non-observation of proton lifetime until 2014, and flavor fits. But of course, flavor fits. This is like another business we didn't embark on it yet. This is just everything, all of magnitude considerations. But this solution, this second solution, looks like problematic at 2 loops at least. And this is the end, actually. If this is the take-home message, that it's almost impossible to calculate proton lifetime accurately, although we are already kind of massaging this unification paradigm for over 40 years. And now we are in a situation of a very good and very well-established standard model at the low scale. And the reason is namely that are namely those 4 things that I was talking about, 3 things that I was talking about, in particular the Planck scale effects. And the other part of the take-home message is that there is indeed, yet there is still a scenario which is that a non-supersymmetric SO10 gut broken by 45, which is very special because it does not have this leading order Planck scale problem. And it's the vast majority of the out parameter space. By the vast majority, I mean in the singly fine-tuned realizations, it says that either one should see a scalar octet at the LHC, or one should see proton decay at hyper K, because I'm discarding here implicitly the substrate solution. So this corresponds to the octet. This is it. Okay, thank you very much for your attention.
Thank you for a very nice talk. There is time for 1 or 2 questions or comments.
So would you say that minimal SU5 has Planck scale problem?
Yes.
Because the 24 does not have the feature of the 45.
Absolutely.
And that probably discards other guts as well, E6.
Yeah. Well, E6 is not a real gut, I would say, because there the problem is that you usually need large representation. There is one aspect that I did not have time to comment on, that, and that's the Landau poles. Because if you have very large representations, then what happens is that you encounter the Landau pole just after the gut scale. And if in your calculations you happen to need a spectrum, a gut spectrum, which is somewhat spread around the gut scale, some of those heavy guys may already live in the domain where we are hitting the Landau poles. So we are losing perturbativity in such a case. So E6 for me, since it relies typically on large representations or on non-renormalizable operators, this all was renormalizable, of course, or on non-renormalizable operators, which means proliferation of couplings, etc., is not a really promising scenario, because there you are quite unlikely to be able to calculate anything. But of course, like concerning SU5, there's no way to get rid of these Planck scale effects. Concerning SO10, there is this unique scenario where you can do that. Concerning the others, I'm not sure. Maybe Renato would know about this, or we can discuss later, whether there is, or which representations they can avoid this Planck scale correction catch in the E6 case. That's a simple group theory exercise.
One question, but in your model, the pooling corrections are very important. So how are you sure that higher order will not affect your?
But they are not large. They are important because they can be bigger than the one you which you mean 2 loops?
Yeah, in the plots you show how it changes the allowed regions.
Yes, that's true. But the higher order corrections we have no access to. Again, because of the higher order Planck scale effects. So 2 loops is the best one can do. But you're right that it may be that the higher order effects, like higher order beta functions, for instance, may do something here. But this is something that one can check in principle.
Yeah, but the effects are still small. What you're doing is that the delta alpha, which itself is a small number, makes an important shift.
Mm-hmm.
But the next order in the delta alpha is again smaller than this delta alpha.
That's right.
So they're still doing perturbation theory correctly, I think.
Well, correctly, that maybe it changes.
Yeah, but this is due to the Caesar effect.
Yeah,
of course, the
exactly.
same Caesar effect would apply to higher loops. But this is something that we can check. Like you can view it in such a way that at the classical level, the theory tells you that the octet should be at the gut scale. So at one loop, it shifts you to 10 to 4 TeV. At 2 loops, it shifts you just slightly lower, and at yet higher loops, of course, it would perturb the result.
Yeah, because we have diminished the error.
Yes, sure. It's a quantitative question. The interesting thing is that the bulk of all these solutions is low energy.
Yeah.
Any further questions or comments? If not, then we thank the student.